Well, hello everyone. Welcome back to the second half of Combinatorics after our extended spring break. Obviously, things have been moving really fast, and a lot of stuff has changed in that since I saw you last, right? That 2 weeks since I saw you last, I think that was March the 4th. It seems like the world is a completely different place, right? Since then. However, I think that we're well equipped to continue the course in a way pretty similar to what we were doing before the break, except we won't be meeting each other face to face, obviously, as the campus is going to be closed. So we're going to have to conduct all of our business online. But since you're already used to having me record lectures, if you've been watching those before the break, then the second half of the semester will be very similar. I'm going to record the lectures in exactly the same way and post them online for you to watch, and then we'll be doing homework just like before from our text, and also we'll be taking tests, of course, but we're going to have to do those remotely. And I'm going to say a little bit more about how you'll be turning in homeworks or how we're going to be taking tests in just a minute. Since we're not going to be meeting face-to-face, that's not ideal, of course. I'm really going to miss being in the classroom with you guys because you're a very good class, and it helps me a lot when I'm lecturing to get feedback from you, right, in the form of your questions, or especially when you make comments and help me solve problems in the class. So that part will be missing, and that's unfortunate, but nevertheless, I think if we're all working together, I think the second half of the semester can be just as successful as the first half of the semester. I know many of you improved your grade on the makeup test, and so I gave right before spring break, right? And so those new grades are posted, right? Unfortunately, I'm not going to be able to return the makeup test to you, right? But your revised exam 1 scores are posted, okay? I think if you are listening to the lecture, that is a really good sign, right? And so that's going to bode well if you've made it this far. However, if you are having hardships, right, or if you are have difficulty with access to resources, right, if you don't have a consistent internet access, for instance, or any sort of problems like that, please contact me, right? And I've the contact information is exactly the same as before the break. My email is the same, right, of course, and my office phone number, if you call that number, I am able to respond to that, okay, even though I'm not going to be on campus, so you can call me as well. I've been sending you lots of emails, and now since we're conducting the course online, I'm going to be sending you a lot more emails. So I'm sorry if it's going to seem overwhelming. I'm going to try not to send you too many, but it's still going to be a lot, okay? Because that's really the only way that I have to communicate back and forth with you. Of course, I can record these lectures, but then you don't get to give me feedback directly, right, during the lectures. So email is really our primary avenue for communicating back and forth with one another. So I will be sending you emails, and I've already sent you several emails. I assume you've read some of those since you're watching this lecture. And those emails are posted as announcements also, of course, in Blackboard. So I did want to just mention a few of these announcements. So these are in your Blackboard page, right? If you didn't get a chance to look at these emails closely, the announcements are there. So this is just the general announcements, right, that the classes are going to be online for the remainder of the semester. And I have created this document, which is just a syllabus addendum, right, with some important information in it, which you can which is also posted in Blackboard. under the class syllabus link, but you can just click on this link too and find that addendum. I've had to update that since I first recorded it, or since I first created it, because things are moving so quickly, and I'm hoping I don't have to update it too much again, but who knows, right, the way the situation is evolving. So basically what that addendum says is, of course, the remainder of the class is going to be conducted online. You are going to be submitting your assignments to me, that includes homeworks and tests, by email, right? And I will be, of course, then posting your grades and hopefully returning those assignments also via email, or at least I will return those assignments also via email. Right? We had a test scheduled for, I think it was April 1st, but we're going to postpone that test, and I think we're going to postpone that test till April the 10th. Actually, let's look at this. Let's look at this syllabus addendum here, and to remind me of this. So I think that I indicated here that we would postpone the first test till April the 10th. All right, so here's the syllabus addendum, right? Okay, and so indeed I postponed the first test till April 10th, and we're going to conduct that. It's going to be a take-home written test, as I mentioned, and you'll be returning that to me via email for grading. I'll still post a practice test for this one, just like we did for the first test. So I'll post that closer to when we're actually ready to take this. So the first test will be on April 10th. However, the first thing that you have to do for me here is turn in homework number 4, right? Okay, so y'all been working for quite some time on homework number 4. I'm going to say a little bit more about some of the problems in homework number 4, namely the section on finite probability here in just a second, okay, when we actually get to the lecture. That is going to be due on March the 30th, okay? And so there are instructions posted on how you're going to get that assignment to me, okay? And so I want to point that out to you right now, right? So our first homework is due on March the 30th. If you go to the homework link here on the, if you go to the homework link there on the left-hand side, right, here are the instructions for submitting homework. So you want to read those instructions. Basically what you're going to do is, write out your homework, right, on paper by hand like you've been doing. So I assume you're doing that currently, right? And then you're just going to scan that homework assignment to convert it to PDF. So you can do that with a scanner, of course, if you have a scanner. But if you don't have a scanner, there are lots of apps that you can download onto your phone, right, where you can take pictures of your work, and then it will convert that to a PDF. But I do not want a picture, right, image sent to me. I want a PDF file sent to me. So you'll need to take a picture of your homework, right, and use one of these apps to take a picture of the homework and convert it to PDF. So there are instructions in here in general about how to do that, right, with one of these apps. I have used Office Lens and Adobe Scan, so they both work really well, and there are free versions of both of these. So, and many of you, of course, are already used to creating PDF documents from your phones, scanning from your phone, so you know how to do this. But if you don't, then these apps are really pretty straightforward to use, right? And then you're going to email that assignment back to me. And that's actually at my regular email address, right, which is, hope I put it in here. No, I didn't, but it's, oh yeah, I did. Here it is. It's wallerw@uhd.edu, right? You're going to mail your homework assignment to me at that address, and then I'm going to open that PDF file, and then I'm going to grade that, right, and then return that to you, okay, and at the same time, of course, post the answers to homework to all your homework assignments, but in particular homework number 4. And so this, again, as I mentioned, this is also the way we're going to take the test. I will post a test. You're going to write out your answers to the test, and then you're going to email me the test, right? PDF version of the test, and then I'm going to grade that and return that to you, right? Okay, so be very actually similar to conducting class face-to-face. You're going to be giving me a test, I'm going to be grading it, and I'm going to be returning the test, right? It's going to be a written test, just like our first test, right? Okay. What, of course, will be different is you'll have a little bit longer time frame to work on the test, right? And so we'll discuss that when we get closer to the first test, what the limitations are on when I'm going to post the test, and then when you have to actually submit the test to me, right? What that time period will be. Okay, so that's not, however, going to be an hour and 15 minutes, so that will be a little bit different from taking the test in class. All right. So again, this document is in the homework link, right? And then that syllabus addendum is here under the class syllabus link there in Blackboard. One thing that I noticed that was in that addendum when we were looking at that there just a moment ago is it says that the labs on campus, the academic computing lab and the library computers and the academic support center computers are available for you to use. And unfortunately, that has changed since I typed that addendum. Campus access now has been restricted, so you will not be able, unfortunately, to access computers on campus if you need to access computers to do your work. So if you are having difficulty with computer access, or if you are having other hardships, right, because a lot of people are in precarious positions right now due to the virus, obviously, so you need to contact me, right? So I'm imploring you, begging you to contact me if you need to, right? And so we can discuss whatever extenuating circumstances that you have, and I can give you perhaps some direction to resources, UHD resources that might be available to you to help you, or we can discuss if you need to, what your options for withdrawing from the class would be, if that's really the only thing that's going to work, right, based on what's going on in your life, right? Okay. All right, so let's go back just a moment here, and I think I sort of said there everything that was in these announcements, right? So there's the first announcement, right, that we're going to have to move things online, right? Here is the announcement that for the due date for homework number 4, right? It's Monday, March the 30th, so a week from theoretically when I'm posting this lecture, right? Okay, and you are going to again scan your written work and email that to me, and then I'm going to grade that and then email that back to you, right? Okay. But make sure you scan it right and submit it to me at this address, right, in the form of a PDF file. So if you're having issues with that, right, or don't understand how to do that, correct, please contact me so you can email me, or in that case, it might be better to phone me, right, so we can discuss it over the phone. If you need instructions on, how to use one of these apps or something. But another great way, of course, to contact me, and so I also encouraging you to take advantage of this option, because you're going to want to ask questions, right, for the remainder of the semester on various problems. So you can also contact me via Zoom, right? So you can download the Zoom app. You can download that to your phone, but there are versions of that also for tablets and for desktops, right? And that's a teleconferencing app. It's very similar to Skype, and so I'm going to be holding office hours via Zoom, right? At my office hours that were normally scheduled, right? And so from 3 to 4 on Monday, Wednesday, I'll be in Zoom for office hours to answer questions. From 9 to 10 on Tuesday, Thursday morning, I'll be there, and then on Friday morning as well, I'll be available. Now, when you use Zoom, you have to use what's known as a meeting ID. So that's just that sequence of numbers that's an identifier, for the meeting. So Zoom puts you in the right spot, right? Unfortunately, because I flubbed this up a little bit, I wound up using different meeting IDs for the different office hours, right? Okay, so you will have to look at these. Depending which office hours you might want to visit me on, you'll have to use a different meeting ID. But you can find this again posted in this announcement on Blackboard, right? Which meeting ID to use. And here are just very general instructions for how to download Zoom, right? It's very easy to use. So I think once you get it downloaded, it won't be difficult to use. I hope. Okay, I don't think so. It's very easy to use. Now, forgot what I was going to say. Please do take advantage, right, of these. Please do take advantage, right, of these virtual office hours, so you can ask me questions. Because since we're not meeting in class, I'm not going to have an opportunity to respond to your questions in class, right? So please take advantage of these office hours. Remember now, these are office hours, right? Okay. The lectures are going to be taped, right? Okay. Well, I know you know that because you're watching the lecture right now. So these are not class meetings, right? These are just office hours, right? You're going to be hearing a lot about Zoom if you haven't heard about it already, because I think many classes are going to be using Zoom for online instruction. So I think if you're not, if you haven't used that before, you're going to start using it really quickly and learn how to use it. But it's going to be very easy to use for us. So I don't foresee that as being an issue, especially since you can use it from your phone, right? There's a Zoom phone app that works really well. Okay. A lot of places all over the world now are going to have to switch to something like Zoom, so to do remote work. So at least for a few months here. So I hope it doesn't crash the system, but I guess that'll be just a giant experiment that everyone's going to be involved in, right? Okay, so I'm sure I forgot to say something because again, there's a lot of information and it's changing here really quickly. So I hope it has stabilized a little bit now that we're going to start the class again. Okay, but we'll see. That being the case, I may have to again email you frequently, right? Okay, so more frequently than you might be happy with having to look at my emails. So please be careful to read your emails, right? Okay, at least look at them. It may not be something that you have to respond to, right? But please be aware of the importance of your email and be reading your emails, right? Not just from me, but from, of course, other people at the university as well, right? Okay. All right. So, well, there's a general idea of how the rest of the class is going to go. Okay. So that's not a great, perfect description. So we're going to have to feel our way a little bit, right? Especially when we get closer to things being due. But remember, your first homework assignment is going to be due on Monday, March the 30th, right? We've been working on that for a long time. So I want to get that turned in by March the 30th, okay? Anytime before midnight is fine, right? But try to turn that in by emailing, again, a scanned version of that to me, right, before March the 30th. Okay, I am going to now launch into a lecture, and because we want to finish what we had started talking about here before the break, and that is finite probability, right? I want to keep track of my time here so that I don't make this this video too long. I tend to run over in time, right, when I get to talking about combinatorics. So I'm trying to watch myself and make sure I don't make the tape longer than it needs to be. Now I know an hour-long tape is going to be not the funnest thing to watch, but for the time being, that's just the best avenue that we have. So please try to be diligent in trying to watch the videos. You don't have to watch them all at once, right? You can watch a few minutes and then come back and watch a few more minutes later, right? You don't have to sit here for an hour and 15 minutes, right, and watch the video, which is different from class, so maybe that's an advantage to doing it online, right? Okay, as you can at least take it in bite-sized gulps. But when I'm taping it, I'm going to have to tape it sort of all at once, because that's the best I can do in this situation. So please be patient with watching the videos. All right, so I'm going to go ahead and launch into the lecture. But if you have other questions, right, email me, phone me, okay, or come to the virtual office hours, right, as posted here in the information which is posted there in Blackboard. All right. Okay. All right. So let's switch back now to talking about combinatorics and in particular finite probability. So again, I had mentioned this right before the break, but I talked about it really quickly. So that's been a couple of weeks. So this is probably you've probably forgotten this by now, or so let me review it a little bit. Now, on the other hand, the topic of finite probability is something that many of you are already familiar with, so you understand the basics of finite probability, and because it really is a very intuitively simple concept. And so if you're already familiar with some of this, then that's great. Okay, you can rely on your prior knowledge. But if you're not really familiar with finite probabilities, then it won't be difficult to comprehend, okay, because it's intuitively a very simple subject. Okay, so recall, right, because I think I said this before, that many of the basic counting techniques, right, that we've been learning in the class, those were developed to help study probabilities, in fact, which is what we're going to be talking about, right? But it's probabilities associated with games of chance, okay? And by games of chance, I mean things like dice and cards, right? The reason people were interested in studying probabilities of games of chance, right, and still are, is that helps them better understand gambling odds, right? So, of course, gambling is a very popular pastime today, as it was in the past, and in particular, it was very popular during the Enlightenment in Europe, which was between about 1650 and 1800. And so, again, gambling was very popular then amongst the royal and the wealthy classes, and I guess amongst all classes, right? The middle classes and the lower classes as well. People like to gamble, but the royalty and the wealthy had, of course, the means at their disposal, right, to hire people to, or to pay people, right, to study these games of chance, right, and that's how the subject of finite probability came about, right, is to help studying gambling odds, all right? And as it turns out, as you're going to see, much of the subject of finite probability is really just counting, all right? It's really just combinatorics, all right? So that's how these gambling odds intersect with our study of counting here and combinatorics. All right, so let me just explain now to you the basic terminology for finite probability. It's very simple, okay? So here's the setting. In finite probability, we think of ourselves as performing an experiment, okay? And I'll say a little bit more about what I mean by experiment. It's not necessarily like a laboratory experiment, right? Like in a science class. But when we perform an experiment, then, of course, something happens, right? When you perform the experiment, it has outcomes. And we're interested in experiments that have a finite set of possible outcomes, right? Okay, so with our experiments, we're going to know, before we conduct the experiment, what all the possible outcomes for the experiment will be, right? Okay, but keep in mind, when you perform an experiment, you just get one outcome, right? You only get one outcome every time you perform the experiment. But we're going to think of ourselves as knowing, or we're going to assume that we know all the range of possible outcomes that could occur, right, when we perform the experiment. And we actually perform the experiment, one of those range of possible outcomes, right, will actually take place, right? Okay, so again, as I mentioned, right, when we use the term experiment, we don't mean a laboratory experiment necessarily, right? We just mean any activity for which the outcome is unknown before we perform the activity, or for which the outcome of the activity is determined by chance, right? Okay, so so we're thinking of when we perform this activity or experiment, we have this range of possible outcomes, but the actual outcome that occurs, right, is a matter of chance, okay, or it's unknown to us beforehand. All right, and of course, what we want to study, right, is what's the probability that one of these outcomes of that possible range of outcomes, right, what's the probability that a particular outcome happens, right, when we perform the experiment. Now, let's introduce a little bit more formal terminology. When we perform an experiment, I said there's a range of possible outcomes. That range of possible outcomes, that set of all possible outcomes, is called the sample space for the experiment. All right, so just think of that as set of outcomes, right, for an experiment, right? And not all the outcomes will occur, right, at once when you perform an experiment. When you perform an experiment, you get one outcome, but the sample space for the experiment is the set of all of those possible outcomes, one of which is going to occur when you actually perform the experiment, right? Now, since we're interested in finite probability, we're also going to assume that, as I mentioned earlier, right, that this set of possible outcomes is finite. We don't have infinitely many possible outcomes for an experiment. There are experiments that do have infinitely many possible outcomes, okay, but we're not going to consider them in this class. We only want to look at experiments where we have a finite set of possible outcomes, and what we're usually interested in counting are one of the things that we're interested in counting when we're computing a finite probability is how big, what's the size of, right, how many things are there in the sample space of an experiment, how many possible outcomes are there when we actually perform an experiment. Okay, now here's the other key assumption, right? So we have a finite sample space, right? A finite set of possible outcomes. All right, now here's another key assumption, which may not always be true for every experiment, but for the experiments that we're dealing with in this class, we have to assume that this is true, and that is each of the set of possible outcomes in the sample space, right? Each of the outcomes from the experiment is equally likely to occur. So when you perform the experiment, we have to assume that any one of the outcomes can occur, right? Any outcome in the sample space can occur, and they're all equally likely to occur. Okay. Again, now that's not always the case when we perform an experiment in general. All right. Some experiments have some outcomes that are more likely than others, but we're going to assume that all of the single outcomes in our experiment are equally likely. All right, so let's convert that statement that I just made there about equally likely outcomes into mathematics. All right, so suppose we have an experiment, right, and we have its sample space. So its sample space here is just a set of possible outcomes for our experiment. I'm going to label the sample space S, and then each one of the possible outcomes for the experiment, I'm just labeling that with a subscripted S here. So S1 is the first possible outcome, S2 is the second possible outcome, S3 is the third possible outcome, up to S sub n is the last possible outcome. So notice that in this sample space there are a little n here possible outcomes, right? Okay, so the size of this sample space is whatever this integer n is, right? And since each of these outcomes is equally likely to occur, right, then when you actually perform the experiment, right, you're going to get one of these outcomes, right? Then the probability that any one of those outcomes occurs, right, is just 1 divided by the size of the sample space, right? Okay, right, because each outcome is equally likely to occur, and when you perform the experiment, you get one of these equally likely outcomes. So the probability of any one of these equally likely outcomes occurring is 1 divided by the size of the sample space, right? So in this particular example, that would be 1 divided by n if n is the size of the sample space. So this is a key assumption in the finite probabilities that we're going to be working on in these problems, right? In this section, right? So we have an experiment. It has a range of outcomes. Each of those outcomes is equally likely to occur. So the probability that any one of those outcomes occurs is 1 divided by the size of the sample space. All right, now usually though, so one other key assumption that it's not really an assumption, but one other key aspect of finite probability is when we are actually performing an experiment, we're often not interested in just the probability that a single outcome occurs, but sometimes we're interested in the probability that some subset of outcomes occurs, right? That means one outcome in a subset is the one that occurs. That'll be a little bit clearer statement when we look at an example. Okay, so if you have a sample space, set of outcomes for an experiment, and you have a subset of that, any subset of that sample space, okay, any subset of possible outcomes, that is called an event for the experiment. That's not an outcome of an experiment, it's a set of possible outcomes for an experiment, and that's referred to as an event. So, because each of the outcomes are equally likely to occur, then the probability that a particular event happens, that is, one of the outcomes in that subset is the outcome of the experiment, then the probability of an event is the size of the event divided by the size of the sample space, right? Okay, so remember, an event is a subset of outcomes, and we say that the event occurs if one of the outcomes in the subset is the outcome of the experiment. So the probability of an event occurring is the size of the subset, the size of the event, right, divided by the size of the sample space. Oh, I didn't mention this notation. Here I put a little p here in front of the event. That just means the probability of this event occurring. So notice just a single outcome from an experiment, just one single outcome from an experiment is also an event, right? Okay, that's a subset of size 1. So its probability, again, remember, is going to be the size of the event, the size of the subset, which would just be 1, and then divided by the size of the sample space, right? So there you get that same probability that we showed before, right? The probability of a single outcome probability of any single outcome from an event is 1 divided by, the probability of any single outcome from an experiment happening is 1 divided by the number of possible outcomes for the experiment. Okay, all right, so well, we better make this concrete here by actually now looking at some examples. So if it's a little bit abstract at this point, that's fine. We're going to make it a little bit more concrete by looking at some specific examples. All right, so here's our first probability computation here. So suppose we just take any positive integer. So this could be 1 or 2 or 3 or 4, right? Okay, and suppose we write down a sequence of integers, right? Okay, all of which are between 1 and this large integer that we chose here, right? So for instance, if we let n be 6, right? And then if we just choose a sequence of numbers, 6 numbers, all between 1 and 6, well, we would get something that looks like this, right? So I can have 5, 3, I can repeat the 5, 6, I can have 2, and I can have 1, right? But notice here, I'm going to stop when I get up to n equals 6 of the integers, right? But notice just the way the just the way this activity was described, right, then notice you have to write down 6 integers, right? So you pick this number n, and then you write down a sequence of integers, right? All of them between 1 and n, but you write down n of them, right? Same number of integers as you chose for this number. Okay, well, that activity is the experiment, okay? Because we're going to write down this sequence of numbers at random, okay? So we're going to think of ourselves as just sort of like I did here, just write down random integers there between 1 and n. So that is the experiment, right? Okay, and because the outcome from that experiment is governed by chance, right? Okay, it's unknown beforehand because we're just writing down the integers at random, and so an outcome from this experiment would end up being one of these sequence of integers, right? So if I was conducting this experiment with n equals 6, there is one of my outcomes, right, from this experiment, okay? But if we performed the experiment a second time, right, maybe we would get this outcome, right? Okay, see there I wrote down 6. Again, I wrote down 6 integers there. This is if n is equal 6, right? I wrote down 6 integers, and all of them are between 1 and 6. In this case, they're all the same number, 2. So that's a possible outcome for the experiment. Okay, so once you have an experiment, right, okay, and then you have an opportunity here for computing probabilities. Okay, so for this experiment where I'm just writing down at random, right, this collection of, writing down at random, right, this sequence of integers, n integers, right, all between 1 and n, then what's the range of all possible outcomes for this experiment, right? In other words, what is the sample space for this experiment, right? And the sample space for this experiment, I'm going to call that S for sample space, right? Well, that's just the sequence of all possible integers, right? A sequence of n integers all between 1 and n. Let me emphasize that. So it really should be S is all possible sequences, right, of n of these integers, right, all of which are between 1 and n. So again, if you think of performing this experiment, right, okay, what you're doing here is just selecting, right, n integers. So I'm sort of filling in these blanks here, right, with integers, all of which are between 1 and n. All right, so let's see if we can compute the cardinality or the size, right, of this sample space. All right, so let's think of performing this experiment, right? Okay, what happens when we perform this experiment, right? Well, we just choose, right, this sequence of integers, correct? So if you're thinking about creating an algorithm for building one of these sequences of integers, right, okay, then, well, you have to do that by choosing the first integer, right, in your sequence. We're calling that I sub 1. That's the first integer in the sequence. And you have n possible choices there, right, because you can put any of those n integers, right, in the first spot. And since the sequences can repeat numbers, notice there's no, in the sample space, right, or in the experiment, there's no prohibition against repeating numbers. That means then when you put in the second number in your sequence, right, you have n choices. And then when you put in the third number in your sequence, you have n choices. And then so on and so forth down to when you fill in the last number in the sequence, right, you have n choices. So altogether, it looks like our sample space here, the size of our sample space is going to be pretty big, right? It's going to be n raised to the nth power, right? We're just going to multiply all these factors of n together. There's n of them, so it looks like we get n raised to the nth power. That is the size of our sample space. See, all the possible outcomes from this experiment, when you just pick at random, right, in integers between 1 and n, well, there's n to the nth power many ways of creating such a sequence. So there are n to the nth power many outcomes for this experiment, right? So that is the size of the sample space. Now, we weren't exactly asked, though, what's the size of the sample space, right? That's kind of an intermediate problem in computing what we were actually asked for here, which is what is the probability that when you perform the experiment, you get a sequence that contains no repeats, right? So we performed this experiment. Of course, a lot of the sequences that could come out of the experiment, if we're just choosing these numbers at random, right, these integers at random, a lot of the sequences that could come out of this experiment are going to have repeats in them, right? But we're interested in the situation where we end up creating a sequence or getting a sequence that doesn't have any repeats here, right? So the event that we're interested in, computing the probability for in this problem is the event that when we conduct the experiment, we get a sequence that contains no repeats, right? Or this event is the set of all sequences, right, that we could generate that don't contain any repeats. That's the event. That's the set of outcomes, right? The set of outcomes is a sequence, is all sequences that contain no repeats. Actually, let me emphasize that. So I should say our event is all sequences that contain, right, no repeats. Okay, so let's see how many outcomes are in this set, right? In other words, how many sequences do not contain repeats. Okay, let's see. So if we're building a sequence that doesn't contain repeats, that's pretty easy to do, right? So let's think of just building up this sequence. Remember, we have to choose n numbers here, so I'm calling those I sub something, right, to represent the n different values that we're putting into the sequence. So if you start building up this sequence, right, well, just like before, you have n choices for the first number in the sequence. But now for the second number in the sequences, you cannot repeat the first number, right, because we don't want any repeats. So in the second place, you only have n minus 1 choices, right? And then in the third place, you only have n minus 2 choices, right, because you don't want to repeat the first two numbers. So you just continue in this fashion, right, down to when you pick your last number, well, you only have one choice there, right? Okay, because there'll only be one number left that you, only one number that left that you haven't used, right? When you fill up the last number in the sequence. So just multiply all these possibilities together, right, and you get, well, not surprisingly, right, that's going to be n factorial, okay? So the number of sequences that does not contain a repeat, right, is n factorial. So this is the number of sequences altogether, right? That's the number of outcomes for our experiment, possible outcomes for our experiment. That's the sample space for the experiment, right? Here is the size of the event that we get a sequence with no repeats, right? There are n factorial outcomes, n factorial sequences that contain no repeats, right? So the probability of this event occurring, right, the probability that we choose a sequence that contains no repeats is the size of that event, right, divided by the size of the sample space. So that's going to be n factorial divided by n to the nth power. I don't think that's going to be a very large number, so I think this is going to be a small value typically. So probably we don't have a very good probability, right, of choosing a sequence that contains no repeats. For instance, if n is equal to 6, then the probability that this happens is 6 factorial divided by 6 to the 6th power. You can compute that and with your calculator, and I think that's going to be kind of a small number actually. All right. Okay, so see, there's our first example of computing a finite probability here, right? You see sort of how that works, and that really sort of involves a lot of counting, right? Because we had to count two different sets there to answer this probability question, right? We had to count the size of the sample space, and we also had to count the size of the event, right? All the outcomes in the event. Okay, well, here's where I left my space here for filling out the probability of p, right? So it's n factorial over n to the nth power. Okay, let's look at just a variation now. So let's just change the event here. Same experiment, so we're just choosing these n integers, right, at random. And we want to know what's the probability that the sequence that we generate, right? If the sequence is generated at random, what's the probability that we get a sequence that contains exactly n minus 1 different numbers, right? Exactly n minus 1 different numbers. So again, if n is 6, let's see what would be a sequence that would be in that event, right? So you just write down a sequence there that has exactly n minus 1 different integers in it. So let's see, we might have 3, 1, 2, 6, 2, 5, right? Wouldn't that match the description? Because if you count the different integers in this sequence, well, there's 3, 1's different, 2's different, so that's 3. 6 is different is 4, but then you repeat the 2, so that doesn't give you a new integer, and then 5 is different, so it looks like we end up with what? 5 different integers there, right? So that would be an event. That would be an outcome in the event, right? That we get a sequence of exactly n minus 1 different integers when n is equal to 6. All right, so let's see what's the probability that something like this happens, right, when we perform this experiment. Not with just n equals 6, right, but with any size there for n. All right, so again, remember the size of the sample space is like in the previous part, right? That's n to the nth power. But now we have to determine, to compute this probability, right, we have to determine what's the size of the event, right? So how many sequences do we there have, right, that contain exactly n minus 1 different integers? So what's the size of that particular set, right, of sequences? All right, so let's think about how we're going to, let's think about how we're going to count B here. So how would we go about constructing a sequence that has exactly n minus 1 different integers? All right, so we're going to solve this algorithmically, right? I'm just going to go through that series of steps, right, that we would use to build such a sequence, and then we'll know how many choices we have for each one of these steps, and then we'll just multiply all those choices together, right? Okay, and that will give me the number of these. Sequences. All right, so let's see. I think the first choice we would make, right, if we were trying to create one of these sequences that has exactly n minus 1 different integers, is we would pick the integer, right, that's going to get repeated, right? Because if you have n minus 1 different integers, that means, since we have n integers altogether, that means one of the integers is going to have to be repeated, right? So let's first pick the integer that we're to repeat, right? So in this example here, when n is 6, the integer that we ended up repeating there is 2, right? Okay, but of course, if you build different sequences, you can pick different integers to repeat. All right, so how many choices there would we have for picking the integer to repeat? Well, that's pretty obvious, right? can choose any of them, right? When you start, you can pick any of the integers to repeat. Okay, so that's the first step in creating one of these. That's the first step in creating one of these sequences. All right, now the second step then is to pick the spots, right? Pick the spots for the remaining integers. Okay, so because you're going to repeat this integer, and so that means it's going to go in two positions in your sequence, right? So let's pick the two positions where we're going to put these repeating integers, correct? So for instance, in this example, I put 2 in position 3, and I put the repeating 2, right, also in position 5, but I could have put the repeating 2 in position 3, in position 1, I mean, and I could have put the repeating 2 also in position 2, right? I could have put a 2 here and a 2 here, and then filled in the rest of the sequence, right? Or I could have put the 2's there at the end, right? Like this. So my next choice there is to pick again the two places where we're going to put that repeating integer. Now that would be picking 2 spots out of the n possible spots, right? So that's going to be a combination. You're going to choose 2, right, of these positions in which to put the repeating integer, and you've got n positions, so you're picking 2 of those n. Okay. All right. So so we're sort of halfway there, maybe, or part of the way there, right, to building our sequence. Okay. All right. Now let's see. Next choice. If you repeat one of these integers, right, exactly once, that means then that one of the integers is going to get left off of the sequence, correct? Because you've only got n integers. For instance, here, notice, since we decided to repeat the 2, right, then that means we had to exclude one of the other integers between 1 and 6. In this instance, we excluded 4. But notice 4 doesn't appear, but we could have excluded a 5, or we could have excluded the 3, or we could have excluded a 1. So you have to pick which one of the remaining integers you're going to exclude, right? And since there's n minus 1 of the integers left, that means you have n minus 1 choices. So again, our third step there is pick the integer to exclude, right? Pick the one that you're not going to include, right, in your sequence. All right, so that integer will be missing. So we don't have to worry about where we place that integer, right, because that integer is not going to be there, okay? It's not going to be in the sequence, just going to be missing. And so finally now, the last thing that we want to do, right, to build the sequence is we pick the integer that's going to be missing, right? We know the integers that we're going to repeat. We know where, right? We know where those integers are going to be, right? Okay, because we've already picked the 2 positions for the repeating integer. All right. So the only thing that's left to do, right, is to fill in the rest of the spots, and you have to fill that in with the rest of the integers that are possible, right? Okay, and let's see, how many would that be? Well, you picked one to repeat, right? So you've used 2 of your n spots, and now you pick the integer that you're going to exclude, right? So so the integer that's going to be repeated has been picked. So we can't use that again. The integer that's going to be excluded has been picked, right? So you can't include that one. So it looks like you just have n minus 2, right, integers left, right, that you have to deal with, okay, that you have to put into the sequence. And those n minus 2 integers can be arranged in in the remaining spots, right, in any order. You just have to fill them in, right, in any order that you like. And so that, of course, just arranging n minus 2 things, that is a permutation. So so to fill in the remaining integers in your sequence, you just have n minus 2 factorial ways of doing that, right? Okay, because these n minus 2 numbers that are left, right, that have to go into the sequence, they can be put in that sequence, in the remaining positions in that sequence in any order, right? So this is just filling in the remaining integers, right, in the sequence. So there's n minus 2 factorial ways to do that. That's it, okay? Once you've gone through all of those steps, you will have created a sequence that has exactly n minus 1 different integers. So you've got those 4 choices to make. So just multiply, right, the number of choices at when you have to make a choice, right? And that would give you the size of the set. So it looks like it's exactly what I wrote here, right? N times n choose 2, right? And then times n minus 1, and then times n minus 2 factorial. Let's see if this simplifies a little bit. Let's see if this computation simplifies a little bit. So I have n times n factorial, n choose 2 is going to be n factorial over 2 factorial, and then times n minus 2 factorial, right? Oh, that's cool. And then times n minus 1, right? And then times n minus 2 factorial. So when you multiply all these factors together, right, you can divide out the n minus 2 factorial, and so that does reduce the calculations a little bit. You get n times n factorial times n minus 1. That's a pretty big number, right? Because you still have, that's still, n factorial is pretty large, right? So you're going to have a large, apparently a lot of these sequences, right, that contain exactly n minus 1 different integers. And now finally, let's just fill in the probability, right? So when we actually conduct the experiment, what's the probability that this event occurs, right? That we get a sequence out of all those possible sequences, that we get a sequence that just contains exactly n minus 1 different integers. And so, well, there it is, right? It's this, the size of the event, right? The size of the event, right, divided by the size of the sample space. So that's n times n factorial times n minus 1 over, and remember the size of S there was n to the nth power. My writing is really slanting backwards here on this tablet today. Okay, so there's your first kind of example of a there of a finite probability. All right, now here's an example that I just started, right, and gave you a little bit of information on, right, before the break. Okay, so so let's see if we can think about starting this probability problem. Okay, so what we want to do here is to count the number of integer solutions, so it has to be whole number solutions to this equation, right? Or we want to consider that the integer solutions to this equation. So a very simple equation, right? You have x1 plus x2 plus x3, right, is equal to 20. So what values can we fill in, right, or what sets of values can we fill in for x1 and x2 and x3, right? So that we add them together, they're kind of about to be 20, but we only want integer solutions, so we only want whole numbers here, and we want them all to be non-negative, right? So we're not going to consider all real number solutions to this equation, right, of which there would be infinitely many, but we want to look at just the integer solutions, right? How many ways can you, how many choices do you have for x1, x2, and x3 that add up to 20, right, where each of those is a whole number and each of them is greater than or equal to 0. Okay, now, what we'd like to do here is think about what I have not described here is not an experiment or event. All right, I've just asked you to, you know, think about the integer solutions to this equation. But once you've thought about those, then we're going to create an experiment. Because what I want to think about is what happens if we have a computer, and the computer is just randomly here generating solutions to this equation, right? Again, integer solutions, non-negative integer solutions to this equation. So suppose we've written a program that will just randomly generate a solution to this equation, okay? And so if we have such a program, what's the probability when the program runs, we'll get a solution where all of the variables x1, x2, x3, all of those variables are greater than or equal to 2. Okay, so you see the experiment. The experiment is to again randomly generate non-negative integer solutions to this equation using a computer program, right? Okay, and then count how many of those, right, would be such that all of the x's come out to be bigger than or equal to 2. Right. See, in general, when we create a solution, our solutions only have to be bigger than or equal to 0. So what happens that when we randomly generate a solution, we actually get one where all of the x's are greater than or equal, not just 0, but greater than or equal to 2, right? So an example of you know, such a solution, right, would be x1 equals, say, 11, and x2 equals 5. I'm just generating one at random here, sort of, and x3 equal to 4, right? Okay, so see, that's a non-negative solution to this equation, right? Because 11 plus 5 plus 4 is equal to 20, but it also has this characteristic, right, that each of your x values is greater than or equal to 2. Now, we could have generated, you know, this solution, right, at random. Probably wasn't very likely to occur, but we could have generated this solution at random, 20, 0, and 0, right? All of those numbers also add up to 20. See, this adds up to 20, of course, and these numbers also add up to 20. But this solution is not the solution that I'm interested in, right? I want to know what's the probability of generating a solution where all of the variables are great, all of the unknowns are greater than or equal to 2, right? Okay. Okay. So that's the setting, right, for this experiment. Okay. All right. So let's talk about how we're going to find this probability, right? So the steps are kind of the same, right? First, you want to write down. First, you want to see. You want to count your sample space, right? So our sample space S is going to be all non-negative integer solutions. Right, so for example, that would include this solution and also this solution, right? And so that's our sample space, right? Because the computer is generating a solution at random, so it might generate any of these non-negative integer solutions as you know, the result of this, or as the outcome from this experiment. And then we've got to count that sample space. All right, so before the break, here's the way I suggested to count that sample space. All right, so we're going to have to do it kind of a little bit indirectly. All right, so here's the trick here. Let's think of a sequence of symbols. All right, and in this sequence, I'm going to have 20 zeros, and I'm going to have 2 slashes. And what I'm interested in is what are all the possible arrangements for that sequence of symbols where you've got 20 identical zeros. Notice they're identical zeros, and 2 identical slashes. So I want to know what are the ways there of arranging those 20 identical zeros and 2 identical slashes. All right, now the reason I'm interested in the arrangements of the zeros and the slashes here is because I claim each one of those arrangements corresponds to a solution to the original equation. Here's why. So as an example, I just wrote down one of the arrangements of the 20 zeros and the 2 slashes. Okay, so of course you can put the zeros anywhere and you can put the slashes anywhere, but here's one arrangement of the 20 zeros and the 2 slashes, right? Notice now the 20 zeros did not come out of thin air, right? That was that 20 zeros corresponds to the right-hand side, right, of this equation. Okay. And the 2 slashes didn't come out of thin air either. Let me show you why. So if you have this arrangement of the slashes and the zeros, this is the solution to the equation that this corresponds to. Count the number of zeros before the first slash, right? In this case, that's 11. That is going to be my solution for the variable x1. And then count the zeros between the 2 slashes, right? Between the first slash and the second slash. That turns out to be 5 here, just the way I've arranged this. So that means that 5 is the value for x2, the variable x2 in my solution. And then after the second slash, right, you have here 4 zeros. So I claim that 4 zeros corresponds to the value of x3 in a solution. Of course, that is a solution, right, to the equation 11, 5, and 4, right? Because when you add up 11, 5, and 4, as I did here, right, of course you get 20. All right. So every time you make an arrangement of the zeros and the slashes, the 20 zeros and the 2 slashes, then you will have a solution to your equation. For instance, here this is also an arrangement, right, of the this is also an arrangement of the 20 zeros and the 2 slashes. You might be hearing my phone ringing because I'm doing this in my apartment. All right. This is also an arrangement of the 20 zeros and the 2 slashes. So this would correspond to the solution x1 equals 20, right? X2 equals 0, and also x3 equal 0. That's the solution that we were already talking about right here, correct? Right, 20, 0, and 0. Because you have 20 zeros before the first slash, and then no zeros between the slashes, and then no zeros after the second slash, right? So if I can figure out all of the arrangements of the 20 zeros and the 2 slashes, then I'll know all possible solutions to this equation, and that will be the size of my sample space. Okay, now we've already solved this sort of problem, right, before the break, where you're arranging symbols, right, where you have several symbols repeated that are identical. And so the way you are going to think of this is as follows, right? If I make an arrangement of these symbols, that's 22 symbols, right? That I have to arrange, or you can think of it as 22 positions in the sequence that you have to fill up with either a 0 or a slash, right? 22, right, positions in this sequence of symbols, right, that you have to fill up with either a 0, right, or a slash. Now, the way we'll decide how we're going to, whether to put a 0 or a slash in a particular position, right, is to think of partitioning the positions into two partitions. One that corresponds to positions that get zeros in them, and one that corresponds to positions that get slashes in them. So this arrangement of the zeros and the slashes is really a partitioning problem, right? You're going to take the 22 partitions, the 22 positions, and you're going to partition them into 2 partitions. 20 of the positions that we'll put a 0 in, and 2 of the positions that we're going to put a slash in. So what we get is a partition problem, right? We've got 22 objects, and we're going to partition it into those 22 objects into 2 partitions, one of which has 20 things in it, right? The 20 positions that are going to get zeros, and 1 partition which is going to have 2 of the positions put in it, right? The 2 positions that are going to get slashes put in. All right, so by the way, I want you to notice, since you only have 2 partitions here, this is the same as, you could write this also as choosing 2 things out of 22, or it's also the same as choosing 20 things out of 22. This number of partitions, since you only have 2 partitions, is the same as a number of combinations. But anyway, notwithstanding, right, we know the formula, right, for this number of partitions. It's going to be, 22 factorial, right, the number of objects that you're partitioning, right, and then divided factorial, and then divided by the size of each of your partition, factorial. So that's the size of the sample space there. That is the a number of ways of arranging the 20 zeros and the 2 slashes, and that then also corresponds to the number of non-negative integer solutions to the equation. So that's the size of our sample space if we randomly generate solutions to the equation. By the way, when you do these calculations, when I did it, I came up with 231. So the size of our sample space is 231. All right, now that's only counting the size of the sample space, right? Okay. But that's not the event, because we're interested in the situation, right? The event that all of the solutions, when we randomly generate a solution, right, all of the unknowns turn out to be bigger than or equal to 2. So how do we count that event, right, where we create a solution, but all the solutions are bigger than, all the unknowns turn out to be bigger than or equal to 2. So this would be an example of a solution that falls into this event, right? Okay, all of the unknowns are bigger than or equal to 2, but this solution does not fall into this event. All right, so the really easy way to count that is to just think of it as follows. Okay. Since you have integers here that are adding up to 20, right? Okay. Think of that as sort of distributing 20 units, 20 identical units amongst the 3 unknowns, right? So you could, for instance, distribute 11 of the units to x1, that unknown, 5 of the units to x2, that unknown, and 4 of these 20 units to x3, to that unknown, right? That would give you a solution to the equation. But since we're interested only in solutions where each of the unknown is bigger than or equal to 2, then we might as well go ahead and think of taking 6 of the units, right? And just go ahead and assign them beforehand to each of the unknowns. So I'm going to go ahead and assign 2 units here, so x1 will be bigger than or equal to 2. 2 units here, so that x2 will be also bigger than or equal to 2. And 2 units here, so that x3 will be also bigger than or equal to 2, right? So we're just going to assume that of the 20 units that we're distributing amongst the unknowns, 6 of them, 2 in each of the unknowns, has already been distributed. That means then you've got 14 units left to distribute. So finding the number of solutions where each of the unknowns is bigger than or equal to 2 is really the same as solving this equation, right? Where you're just adding 3 numbers together and getting 14, because you've got 14 of the units left to distribute if you pre-distribute 2 of them to each of the unknowns. So what I'm saying here is the number of non-negative integer solutions, right, to our equation is going to be the same as to the original equation with all of the unknowns bigger than or equal to 2 is going to be the same as just the number of solutions to this equation, where each of these is just bigger than or equal to 0. So you're back to just finding a number of non-negative integer solutions to an equation. And we know how to do that, right, from the previous example. So the size of B, it turns out, if you follow this prior example, you're going to end up with partitioning 16 objects, okay, into two partitions, one of them with 14 elements and one of them with 2 elements. Again, because I'm going to think of lining up a bunch of zeros and ones, a bunch of zeros and slashes, 14 zeros and 2 slashes, so that every arrangement of the zeros and slashes, right, would give me a solution, would correspond to a solution of the equation. Yeah, there's an example, right, of 14 zeros and 2 slashes arranged. So this would correspond to x1 equal 6, x2 equals 6, and x3 equal 2. That's a solution to this equation. So where x1 and x2 and x3 sum up to 14, right? So how does that correspond to a solution to our original equation, right, where each one of the unknowns is bigger than or equal to 2? Well, just take these 3 values, right, and add 2 to each of them. Because remember, we're assuming that 2 of the units have already been distributed. Does that add up to 20? Sure, right? See, I just took the 6 and the 6 and the 2 and added 2 in each case, right? And these 3 numbers indeed add up to 20, right? So this solution to this second equation, right, corresponds to this solution to my original equation. And we know from the prior example that there are this many solutions, right? This many solutions, right, to the to this equation. So in your event, you have this many solutions to the original equation, where each of the unknowns is bigger than or equal to 2. Let's see, what is this reduce to? This reduces to 16 times 15 divided by 2. So that looks like, if I can squeeze it in here, that looks like 8 times 15. And 8 times 15 is 120. Ooh, can y'all see that? 120. So that's nice. That means then that the probability of my event, right, the probability I'm going to get solutions, I'm going to get if I generate a solution at random to this equation, the probability I get one where all the unknowns are bigger than or equal to 2, that turns out to be 120, right? The size of the event, right, divided by the size of the sample space. So that looks like it's 120 over 231. So a little bit bigger than, just slightly bigger than 1/2 if you simplify that, if you estimate that with a calculator. Okay, all right, so I'm going to stop at that point because I think I've used up all of my lecture time, right? Okay, and so on Wednesday, I have one more example here of probability. So we'll start with that example in Wednesday's lecture, and then we're going to switch gears from counting a little bit and talk about another topic in Combinatorics, which is called the Pigeonhole Principle, right? So I'll see you again on Wednesday. Remember, you can attend my virtual office hours, look for the announcement in Blackboard, or you can email me, or you can call me, okay? All right? So keep working on that homework number 4 so we can get that done by next Wednesday. I'm sorry, next Monday, right? The 30th. All right, so see y'all guys again on Wednesday.